Right, we've got the S1 International Paper Jan 2019. It's a probability distribution question. I've just got the first part of the question up first. Some children are playing a game involving throwing a ball into a bucket. Each child has 3 throws, and the number of times the ball lands in the bucket is recorded. The results given in the table. So 16 of them missed every single time, and 3 of them got all 4 in. 4 of them got all 3 in. So well done them. We've got to find X bar, so it's like the mean number of times they got it in. So we want the total number of times they got it in. Well, 16 of them didn't get it in all. 36 got it in once. 24 got it twice. So that's sort of the number of times the ball went in. Divide that by the total number of attempts, total number of kids really. And we get 96 over 80, which is 1.2. Right, Sandra decides the model again by assuming that on each throw, the probability of the ball landing in the bucket is 0.4 for every child on every throw, and the throws are all independent. The random variable S represents the number of times the ball lands in the bucket for a randomly selected child. Right, so complete the probability distribution for S. So the probability they get 0 in, that means they've got to miss each time. S is equal to 0 means they miss each time. It's going to be 0.6 to the power of 3. So they miss, which is 0.216. Probably they get 1 in. Well, they're going to get 1 in, so there's 0.4, but they've got to miss twice. But there are 3 ways of doing that. So they could get the first one in, the second one in, or the third one in, which is 0.432. Probably they get 2 in. Well, again, there's 3 ways to do that, because it could be the one that they miss, the 0.6, could be the first, middle one, or the last one. So it's 0.4 squared times 0.6 multiplied by 3, which is 0.288. And the probability they get all 3 in is 0.4 to the power of 3, 0.4 cubed, which is 0.064. This, of course, is the binomial distribution, because we've got the probability the same each time, a fixed number of trials. They're all independent, so 0.4 for every child on every throw, and throws are all independent. So this is actually a binomial distribution with N is 3 and P is 0.4. Right, Ting believes the probability of the ball landing in the bucket is not the same for each throw. So as they have more throws, first throw they're not likely to get it in, but they're more likely to get it on the second go, and even more likely to get it on the third go. So he reckons that the probability that they get it on the first throw is the first one is 0.15 times 1 plus 0.10. Probably get on the second throw in is 0.15 times 2 plus 0.1, and the probability to get it on the third throw is 0.15 times 3 plus 0.10. The language, I think, is quite difficult. The PI is the probability that the ith throw of the ball by any particular child would land in the bucket. And you've got to sort of translate it a bit, really, I think. But he's basically saying it's going to be 0.25 for the first throw, and then it'll increase by 0.15 for the second throw, and increase by 0.15 again for the third throw. And we're going to do his probability distribution as well. So, like I say, the probability to get in the first throw is 0.25. Probably getting the second throw in is 0.4, because it's 0.15 times 2 plus 0.1. Probably getting the third throw in is 0.15 times 3 plus 0.1, or 0.55. And then it starts getting to be complicated now. Probably they miss all 3 times is going to be 0.75 times 0.6 times 0.45, because these are the probabilities that get in on the first, the second, and the third go, which is 0.2025. They probably get one of them in. It might be the first one goes in, so it's 0.25 times 0.6 times 0.45. So hit, miss. But then it might also just get the second one in, so a miss and a hit, and then a miss. So 0.75 times 0.4 times 0.45, or they get the third one in, and it looks like that. Miss, and a hit, and you get 0.45 for that. Probably get 2 in. Well, it might be the first 2 that go in and misses the third time. So 0.25 times 0.4 times 0.45 might be the middle one that misses, or it might be the first one that misses. When you add all those together, you get 0.2925. And the probability to get all 3 in is just 0.25 times 0.4 times 0.55, which is 0.055. Quick check, all these do add up to 1, which is what we'd expect. And then it said, state given a reason whether Sandra's model or Ting's model is the more appropriate for modelling this game. Now, the relative frequencies, looking back at the table at the start, 20% of the kids didn't get any in. It was 16 out of the 80. 45% got 1 in, 30% got 2, and 5% got 3. Comparing it to Sandra's probabilities, it's not too bad. Not too bad. It's not a bad effort, Sandra. Ting's, though, is much closer. That's nearer to 0.2 than 0.216. You got that bang on, and that's nearer to 0.3, and that's nearer to 0.5. So they're all these are better than Sandra's effort. So we're going to choose his method because his ways were closer.